Okay, so let me go to the next criterion. So identifying confounders using the statistical models. Why is it important to do this kind of statistical model? It is because regression modeling is one of the ways by which you can adjust your variable. It is not the only way. There are many other ways. You can do propensity score matching. You can do stratification. So you can do all of these things, but regression modeling is one of the easiest way to control your variables, particularly when you have a lot of adjustment variables. And notice that I'm not saying confounder variables, I'm saying adjustment variables. So these adjustment variables could mean a lot of different things. It could mean confounders, it could mean risk factor for the outcomes, right? So generally speaking, when you have a confounder and you are adjusting for that, you are getting unbiased estimates. That's correct, but that does not necessarily mean you are getting the best standard error estimation. When you are adjusting for your risk factor for your outcome, generally then your standard error shrinks and the confidence interval that you get is usually less wider. So in a sense, controlling for more variables other than your confounders are sometimes okay. Only problem is under some theoretical conditions, if you have a very strong instrumental variable and you are trying to adjust for that variable, then your confidence interval will blow up. You will induce some bias in your analysis as well. So always try to be skeptic about the variables after including which you are getting wider confidence interval. By wider, I mean much wider. So whether your confidence interval is blowing up after including that variable. So try to be always skeptic about that. And it does not necessarily mean that including instrumental variable is the only reason for that. If you have a variable, if you have a bunch of variables which are multi-collinear or highly collinear with each other, that can be another reason why you would see something like that. And also, say, for example, when you are dealing with enhanced study and you have, say, for example, 30 variables and going through each of these variables is probably not that hard. But when you are dealing with very large number of covariates, say, for example, 100 or 200, then going through one by one manually might be very hard. And that is one reason why statistical modeling could be, or machine learning modeling could be helpful. So what are the popular statistical methods that we are generally using? We are using the, we are using this univariate selection of covariate, which is probably the worst method ever. But this, if you look at any paper that is published in any public health journal, that is the first thing everybody does. Even if I submit a paper there and I do not do any univariate selection, then the reviewer keeps bugging me. Where is that univariate selection? Why did you skip that step? The problem is when you have a multivariate model and you have included a variable that was deemed to be insignificant in your univariate selection, that variable might still have some value when you adjust for some additional variables, and that variable might be significant then, right? So if you are going to do multivariate selection, why do you need to go through this univariate selection? And there are some good reasons for that as well, because you want to have a very good understanding of what is the relationship between each of these variables with your outcome. And then when you are investigating that, you can try to figure out whether there is some problem in the coding or there is some problem in the way you have categorized that variable. And sometimes by merging the categories, you can solve that type of problem. So in that way, univariate selection of covariate, or the process of trying to see each of the variables one by one, has some value for checking whether there is some specific concern about one particular variable. But other than that, if you are doing a backward selection model, doing a univariate selection of covariate is almost always useless. All right, so there are a lot of different ways you can do your multivariate selection. One is backward selection, one is forward selection. My understanding is that you are familiar with both of these approaches. It is usually encouraged to use some sort of criterion based selection instead of a p-value based selection, even though there has been some equivalence that was showed that if you do a p-value based selection and if you do a AIC based selection, under certain conditions they can be producing very similar result. And in some sense, if you are trying to deal with this variable selection, one of the consequences is that you are doing a lot of multiple testing and you are not really taking that into consideration, and that will cause you some post-selection issue. That means that it will impact your standard error in a way that you don't want. So sometimes your standard error might not be valid after all of this variable selection. So what is the way? In your stat 400, you have already learned that you have to do this backward selection or forward selection to do your model selection. And now I'm saying that this is not a very good method. So the general answer is when you are doing epidemiologic modeling, statistical criterion is not going to give you any answer. Your epidemiologic answer, understanding of the context will give you the answer most appropriately. So how come we are talking about the statistical approaches? Say, for example, you have already 10 important variables that you already know that needs to be adjusted, because in the literature, it is supported that those 10 variables are confounders. No matter what your backward forward selection tells you whether these variables are important or not, you need to have those variables because you already know that those are important variables and you need to keep them. Sometimes it is possible outside of those 10 variables. Say, for example, you can have another 5 variables that you think are useful in your analysis, but you do not really have a good understanding whether they are your confounders or not. But you have them in your data set and you want to check whether those have any value after you add them in your analysis. Then you can do this backward and forward selection without deleting those important 10 variables. You can do this, whether adding these 5 variables are increasing any value in your analysis or not. If your literature already tells you that these 10 variables are confounders, why do you need to think about those additional 5 variables? Because if you do not explore these additional 5 variables, you are not advancing your science. You are just stick to whatever the literature is saying, and you are not trying to discover any new variable that can also impact the analysis relationship of your interest, right? So it is also important to try to figure out whether these additional variables have any value or not. All right. So since we have talked about this post-selection bias and things like that, one of the things that can help us is data splitting or cross-validation. And there is an alternative bootstrap method called the majority rule. That part will be explained in the missing data analysis lecture. So those we will explore later on. All right. So this is a very controversial one. So when we are dealing with some epidemiologic approach to find out a confounder, often you will hear about a method known as the change in estimate. Whether adding one particular variable is changing 10% of your exposure variables impact, right? And this is controversial in the sense that you are basically relying on empirical data to try to identify whether you have 10% change or not. And that is something that is somewhat dangerous, right? And especially for the variables that you are not sure about, maybe you can use it for them, but you should not use it on all of the variables where you already know some variable is important to try to identify confounders in this way. And most importantly, if you are dealing with a binary outcome, or a survival outcome, that means that you are dealing with a non-collapsible measure. In that case, this method does not work. This method only works in a continuous outcome regression. And also, who came up with this 10%? So it could be subjective. All right, so this is a topic that I will explain a bit later when I discuss with you about the propensity score. But the main idea of this high dimensional propensity score is that say for example, when you work with pop data, then you work with developing your exposure and developing your outcome and some of the covariates, often based on some of the ICD-9, 10 codes. But other than some of the useful ICD-9, 10 codes, there are a lot of other ICD-9, 10 codes that are regularly collected by the insurance companies. And we generally do not use those information into our analysis. What this HDPS algorithm does is that it tries to find out some useful information out of those vast information that we do not use. So we will get to that when we talk about propensity score analysis later. All right. So when we are dealing with machine learning methods, there are some of the methods that can handle identifying important covariates. Say, for example, lasso is one method, random forest is another method. There are some other methods of causal discovery. But the problem is the main focus of these type of models is predictive, right? And if you are trying to use these methods in the context of causal inference, there are some specific approaches known as TML approaches and things like that. Under this framework of TML, the targeted maximum likelihood estimate, you can try to incorporate some of these advantages of machine learning. But other than that, generally speaking, these machine learning methods are more geared towards your predictive model. One of the points that Andres mentioned, I should probably highlight a bit more as well, is that all of the methods that I'm talking about here, I am not really that much concerned about predictive ability. I am more concerned about causal inference from all of these methods, because when we are doing epidemiologic analysis, we are generally interested about a outcome and a primary exposure of interest and the relationship between these two. If this is our framework, then causal framework is the best way to go. Predictive model is something else, where I do not necessarily care about any primary exposure. Whatever exposure or whatever treatment or whatever covariate is improving my predictive ability would be of my interest. I do not need to think of all of these. I simply put all variable that is available in my machine learning algorithm and let it decide whatever is improving my predictive ability.